Here I talk about the process corners. So usually the foundry provided models, they will have these two letter, okay, sequence. So for example, TT, SS, FF, FS, SF. The first letters refer to NMOS. Second letter refer to PMOS. Okay. So what TT means is that NMOS is typical corner, PMOS is typical corner. All right. So what is the FS? Fast, fast NMOS and slow PMOS. So usually the fast PMOS means the threshold voltage is higher or lower. Fast device means threshold voltage is lower, right? It's lower, yeah. So that's right. So that's usually what that means. All right. So if I plot this NMOS and PMOS, right? So basically what they are doing is that. So let's say NMOS has some variation, right? So let's say this is the threshold voltage. Let's say, of course, it's applied to anything, right? Mobility and things like that. So let's say this threshold voltage. So let's say NMOS has this minimum and maximum value, and PMOS also have the maximum and minimum value, right? And of course, there will be some intermediate. That's usually what we call the typical, right? So TT corner is this point, right here, right? Typical. Okay, and then so this is so what is this corner? So this threshold voltage. So the high threshold voltage for NMOS and low threshold voltage for PMOS. So this is what corner? SF. You get that? This is the SF. What is this? Fast corner, right? And this is SS, and this is FS. Okay, so that's how you check. So basically, when you in the future when you run the corners, you're basically just trying to see what's your boundary condition and plus the typical in the center. Okay, so here's a question: when TSMC manufacture this device for you, would that be in this 5 dot? So it will be somewhere in between, right? So it'll be more like this, right? And hopefully most of them will center in the middle, hopefully, right? But then some can be outlier to there. And the reason why we check the boundary condition again, because remember, you need the design margin, right? So that's how you set the design margin. Okay, so you say, oh yeah, the hope is that, if you check your circuit work here, 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 and here, then the probability that all this will work is probably very high. Does that make sense? So that's a boundary condition. Okay. So in the future, you may see some even more extreme case. So sometimes people will say, okay, it's FFSS, like a double or triple F, triple S. So you might see that kind of extreme case. Guess what they're doing? Guess what they're doing? You understand that in the end, it's all probability, right? Basically, what TSMC or all the foundries, what they are doing is statistics, right? You think about this as billions of transistors. There's no way they can find control each individual, right? So they look at this and look at, oh, what is all this billion transistors? What's the distribution? Do you agree that because it's statistics, some of them will be outlier? So in the future, so it depends on the company. Some companies say, oh, I need very high yield. So it means that even if there's an outlier here, I want to sell to the customer for that chip. So what do they do? So they will have this extreme corner, right? Remember I talked about double FF, triple FF. Basically, that's what they're doing. So they are extending this boundary. Okay, so you might be running into that kind of scenario in the future, especially if the project you are working on, the company you're working with is doing super volume, high volume production, like cell phone. High volume production. You don't want to lose any chance to make money. What you do is that you make sure your circuit can work at all corners, all extreme corners. Okay, so this is what I meant, right? It's all come down to EO issues, and EO is everything. Even if you think that's 1% difference, who cares? But just think about how many iPhone in the world. If just 1% of that is a huge profit difference for the company, right? So, okay, so that's the process corners. Next, I'm gonna focus on the so-called local matching. Okay, this is the part where it will affect our circuit design a lot, and this is also something that you and I can more or less understand and control it. Okay, the process corners, they're, it's more like global effect, right? So all the transistors are like fast or slow, right? But this local, it will have certain characteristic to our circuit design. Okay, so basically local variability will affect the matching of our circuits, and it will affect our performance dramatically. Okay, those local matching, is a combination of the random fluctuations, basically a bunch of local random fluctuation, right? So, when you have two transistors next to each other, right? I want them to be identical, right? Then you want everything to be identical. You want your doping to be identical. You want this line roughness to be identical, right? Unfortunately, they cannot, right? And they all handled by different processing steps, right? Remember I talked about etching, right? And doping, right? They are all different mechanisms. So you can pretty much think of that as an independent random process, right? So this is how your class on random or the probability class can be coming to rescue, right? So you can use those to analyze, how good or what's the yield that you can achieve. Okay, so intuitively thinking, feels like bigger area will include more independent random variable, right? Because larger area, there will be more randomness. It's like you composite, right? You aggregate all the different random variables together. So that is true. However, when it comes down to the design, when you do the layout, should I draw it big? Should I draw it small? Okay, so we need to be a little bit careful because the answer is not that easy. It really depends on what you care. In general, if you care about the variation in the relative sense, larger area will average out the random effect, which means that you cannot have a smaller variation. However, if you care about the variation in the absolute sense, the bigger area will actually have more variation. So it really depends on what you care about. So for instance, let's say I'm trying to draw two resistors, R1, R2. If you are in the first bullet here, you say, okay, I care mostly on the relative errors between the two, which means that you care about R1 over R2. If both of them are 10% higher, I'm okay. So that means that you care mostly on the relative error, right? So in that case, the larger the area that you draw this resistor will be better for you. However, in some cases, you say, no, I'm not just caring about these two. I care about what's the variation on the absolute value of that resistor. in that case, if you make this larger, you're gonna have more variation on this absolute value. So let's say I want to make this 1 kilo ohm. You make a larger area, and that kilo ohm, 1 kilo ohm can be very more, can be go to 1.2 kilo ohm, for example, right? So it really depends on what you really care about. And then that really comes down to, your circuit design. Okay, so I will give you some examples. In general, if you design, for example, the differential circuits, usually you care more about the relative ratio. Okay, the left and right, so there's a differential circuits, right? Let's say if I build this differential circuits, right? This amplifier, right? So differential amplifier, so you pretty much care a lot on how the relative matching between the two. However, if you build, hey, this is the filter like this, you care about absolute value, right? Because R and C, this R variation will cause the pole frequency. So that's among some of the examples, right? To show you when and in what scenario you care about what. You care about absolute value, or you care about the relative value between those. Okay. So this is a resistor, and of course, transistor, even if you make they are side by side, they won't be exactly the same. Okay. So one of the most important, as you know, the MOSFET, the threshold voltage will actually change a lot of your behavior, right? Because that's your IV relationship, dictates a lot by the threshold voltage. Okay. So the threshold voltage difference of the MOSFET is one of our big concerns. Okay. So of course the threshold voltage, here, depends on, for example, the doping concentration and oxide thickness, epsilon, right? Permittivity, W and L, okay, and all this are gonna come into play to affect the variation on the threshold voltage. Okay. Turns out that this threshold voltage fall into this average sense. So more like average out. So you have a larger plate. It actually can help on the deviation. So larger W and L. So that's the area of the channel. So all the different doping variation, right? Remember I talked about different random process, right? All this, and you get average out, then your final total threshold voltage, that variation will be smaller. Okay, so larger area would, in general, will be helping. So and all those process parameters. But by and large, the view of this actually turns out to be quite simple. Basically, it's a factor divided by square root of the area. Okay. Later on, I'm gonna show you a lot of all this variation actually all follow the same trend. You make a larger area, the matching, the threshold voltage in this case, it can be captured by this process-related parameters. Okay, so different process will have different A factor. Okay, a lot of times, in the PDK document, they will tell you. Okay, you can read the document. They will tell you, oh, in terms of matching, yeah, this is the factor you're gonna get. If you use our technology, right? So then that becomes very easy because you can back calculate, what's your tolerance on that threshold voltage, let's say difference, right? Standard deviation. Then you can calculate what's the area that you actually need to do. Okay. So this is one of the proof, and by the way, this will be one of the paper which I'm gonna upload to the website. Marcel is a scholar, and then he discovered this simple perspective, right? So he basically is saying that, okay, you can pretty much just model by these factors. And what he did, he taped out a bunch of different sizes of the MOSFET. That's what he did. I think that was in 80s or 90s. I think it's probably 80s. So then he came up with this result and surprised the whole community. He said, "Oh, it's how come it's so simple?" It's so simple. So he used, at the time, he used a 0.18 micron CMOS, and you can see this is W and L. You see WL. And then just a bunch of them, and you plot them. It turns out there's a nice, linear regression here, which is basically inverse proportional to the square root of the area. Okay, so that simple view actually changed the way how we see and how we design the circuits. Okay, so that was a huge contribution from him, and he is a very nice guy. I talked to him a couple of times. Yeah, he's a really nice guy, European guy, and yeah, so he actually discovered this at the time. He was talking to so back in 80s, 90s. He not too many people actually understand how to design the circuits well, right? So then he started to talk to a few people in our community, and that's how everybody right now cites his paper. Okay, I'm gonna share his paper with you as well. Okay, so all this trend. Basically, you can see this standard deviation, right? So if your area you consider is small, you expect more threshold voltage deviation. Okay, when you do the match. Okay, and then it just comes down to the ABT factor, right? So we understand, when you design, this is what we can control, right? Because you control the size of the transistor. Make sense? You don't control. You and I do not control the doping or whatever. That's determined by the process engineer, right? But what we can decide is this. However, even though we cannot control those process parameters, we can still understand, across different technology nodes, how does this matching factor would change, right? So in general, it's actually affected by the gate oxide thickness. Okay, so if the gate oxide thickness reduce, you see this A factor reduced. Is that good or not good? Do we want A factor to be, the ABT factor to be large or to be small? Small. It does go down. That's good. So usually when you go to more advanced node, this will go down. And that kind of makes sense, right? Because you see the reason why they can go down is because they must be able to control their processing step a bit better. Otherwise, how can you make it so compact, right? So it will go down. Okay, but unfortunately, you see, they kind of start to plateau a little bit. So it's not like infinitely go down. So that's one of the trends that we're seeing. Another thing to keep in mind, how even on Monday I talk about, okay, when you scale down, the matching become worse. But then here you see that, okay, Mike, what are you talking about? It looks like this factor seems to go down. The problem with the matching is because when you scale down to lower technology node, your W and L goes up or go down? Go down. The problem is that, if your A factor does not go down accordingly, we still lose. You see that? Because our W and L right now is all scaled down very aggressive, right? But if your A factor does not scale down as fast or even more, then we lose. In the end, we lose. So unfortunately, that's generally is the case for us. So that's why this is what people say. When you scale down to smaller technology node, our analog circuit looks still bulky compared to the digital guy. Why is that digital guy can scale down so quickly? You look at what's the digital library they usually provide. Inverter, right? NAND gate, NOR gate. So let's talk about inverter. Okay. Have you guys seen this digital library? So they have different size, right? So inverter, they have a 1x, 2x, 3x. Okay, so you guys know about this. So what is the inverter 1x? What does that mean? Minimum size. You see that? It does not matter what technology node. usually when they design the digital library, when they say inverter 1x, that means that you are using absolutely minimum size. That's why they go down. They keep go down, right? Your WL, your layout become more compact, everything go down. That's why digital guys are always happy. Of course, now they are less happy because AI are replacing their job right now. It's, okay, you can do it 1x. What do you mean? I'm AI. I can also synthesize those 1x, right? Okay, so the analog guy usually is less happy because we cannot enjoy. We cannot just say, oh yeah, so now this 40K scale amplifier, that's just you go down by like that. Good luck with that matching, right? So you cannot do this. So relatively, usually you look at the analog and digital portion. No matter how you scale down to different technology node, the analog part always occupy some space, right, or significant space. But also that's good news, right? But significant, that means that they need to hire people like you guys. Somebody need to design those, right? So you have a job opportunity always there. Okay. All right, so here's some examples. So the guy I talk about, he actually captured all the different technology node, and then he calculate, so based on that equation, right? So he actually derived. He say, okay, yeah, I'm gonna treat that as a random variable or random process, and he do the averaging based on that equation I showed you earlier. So he was able to match pretty well. So that's whatever that he calculated and the measured, actually they match pretty well. And that's how he became very famous. He said, okay, I was able to match the physical, like physics kind of phenomenon to whatever that I actually measured, right? So right now, you can imagine all the processing steps become so complicated. I don't believe that we can just use that equation to calculate. Yeah, if I see him next week, I'm gonna ask him again whether you actually, not next week, next week. Yeah, to see whether he actually captured this, but I doubt. However, this become a common practice right now. Doesn't matter which node they are doing. The foundry, I told you the PDK, right? They will give you this ABT factor, right? Because you just do a linear regression, right? You just do back calculation. You say, oh yeah, let me just interpolate this, extrapolate this. Okay, that's the factor for this technology. So now it's become a common practice. So the exact mapping to the physical parameter, doping density is less important right now, right? So the bottom line, especially for the circuit designer, that's all we care, right? You never really start designing a circuit and say, okay, yeah, tell me what's the doping density. I mean, who cares? Right? All you care is more like, okay, tell me what's the threshold voltage, right? That kind of thing. Okay. So this is the one of the challenges, right? I told you that I think was it last week or Monday, that over different technology node, right? So let's say 0.25 micron, 0.018, now to all the way to 32 nanometers. The power supply goes down, right? So in the old days 5 volt, right? And now it's sub 1 volt, right? So we're going down quite a bit. However, as you go down, and if you assume that you shrink your analog circuit just like digital circuits, your threshold voltage variation will go up. Even though, as I said, ABT, they also go down, but the square root of the area go down even more, right? So you're gonna have this trend. So this will going up, right? So you see before maybe 5 millivolt, and now maybe 10 millivolt variation. You see this? You don't have too much headroom, right? Because your headroom keep pressed down, but your variation is more and more. Okay, so this is really the challenge for circuit designer, especially analog circuit designer, right? So as your matching become worse, you're gonna have more variation. But that's my maximum, is my VDD. VDD is capping the maximum that I can go, right? So if you're off too much, there's really not much that we can do, right? So that's really the kind of the reality that we are facing. Okay, so so here's one examples, right? So so let's say I want to do a current matching, right? So let's say I have a MOS transistor right here, and this is M1, this is M2, and this ID1, this is ID2, okay? VGS1 and VGS2. Okay, so if I lay them out, exactly the same size, so I want everything match. ID1 equal to ID2, right? And VGS1 equal to VGS2. But however, because of the mismatch, right, here, so it won't be exactly the same. So VGS1, assuming that the square law device, okay, it will be VTH1 plus square root of ID1 over beta 1. And VGS2 is VTH2 plus square root of ID2 over beta 2. Okay, so if I do a current mirror, right? So what is a current mirror? So you tie the gate together, right? Gate together. So your VGS1 equal to VGS2. Do you agree? Because I do the current mirror. Okay, so that means that your VTH1 plus square root of 2ID1 over beta 1 will be equal to VTH2 plus square root 2ID2 over beta 2. All right, so here, I have ID1, ID2, and I'm gonna call ID2 equal to ID1 plus delta ID1. I'm gonna call delta VTH2. Okay, no, sorry. Now let's go back to this equation on the left. So VTH1 plus that square root, right, equal to VTH2 plus that square root. So you have VTH1 minus VTH2 equal to square root ID2 over beta 2 divided by minus 2ID1 over beta 1. All right, so I'm gonna call this as a delta VTH here. Okay, so delta VTH here is square root, so this equation. So I'm gonna factor out 2ID1 over beta 1. So this will be square root of 1 plus delta ID1 over ID1 divided by 1 plus delta beta 1 over beta 1 minus 1. Okay, so if I do a Taylor series expansion on this, which basically square root of 1 plus x is roughly equal to 1 plus x over 2. So I want to factor out this term, right? The square root is more complicated. So you're going to get delta ID1 over ID1 equals to delta beta 1 over beta 1 plus 2 times delta VTH over VGS1 minus VTH1. Okay, so basically this shows you that this kind of analysis shows you that if you are doing the current mirrors right here, you're gonna end up with some delta current right here, right? And of course, you want this to be as small as possible, right? Right now, if you want to minimize this deviation in percentage, right? So how much are you vary by 1% or 2% or 5%? Okay, so let's say your goal is to really minimize that. After you do this circuit analysis, by the way, the reason I go this quickly because this is just like 536A, right? So you can do this exercise yourself. But the bottom line is that what it comes down to is that the current errors depends on your beta error. What is the beta? Beta is mu C ox W over L, right? So your beta errors, or your mobility errors, your W over L ratio errors, so that will affect, okay? The second factor, which is a big factor, is your threshold voltage difference between that two. Remember that delta, the AVT over the square root of area? That's the factor is gonna kill you, okay? However, you see this kind of interesting, right? So whatever that 2 times delta VTH is gonna be divided by VGS minus VTH. What is this? What is the VGS minus VTH?
The order.
VD set. We can control, right? When you design a current mirror, you control what's the gate voltage, right? In this case, if your goal is to minimize that current mismatch in terms of percentage, what should I do? When you design, how should I?
The extreme saturation.
So I should make the VD set large or small? Large. And by the way, that's what people do. So even if you say, hey, I'm using the same sizing for the current mirrors, if you want to make sure that current match is really well, then you use a larger VD set. What's the downside if I use a larger VD set for the current mirror? The headroom issues, right? Because your output, you may not have headroom to sustain that in the situation. Okay. That's what I meant by why we are learning through all this analog class, because it's gonna help you, right? To give you insight, right? Even if the, as we know, right? The square law device is no longer accurate. We know for sure it will not be accurate. But who cares? All I need to know after I do the analysis, all I know is that, okay, I just need to increase my overdrive voltage. And that already helped you a lot, right? So I hope that, that's really is one of the big reasons why you are still taking this circuit class, only for that, right? Because right now, it's a joke that, we can just apply the equation when we match our SPICE simulation. In the old days, that was the case. You know how difficult when I was student, every time I do the homework, it's like pulling my tooth. Because at that time, the SPICE model can actually match my calculation. So that's what we do. We have 2 parts of the homework. One part, you do all the math calculation. The other part, you do the SPICE. This 2 has to match within 10%. Whoever off by more than 10%, you're out. This 0 point. Okay, and now, not anymore, so I'm not torturing you anymore. I'm doing this exercise. But, having this trend analysis is still can be quite useful. Okay, any question? All right, if not, see you next week.